So this video deals with equilibrium. We're in a new chapter now, and it's a very important chapter. It sort of provides the foundation for the remainder of the course. Um, and equilibrium is an important sort of concept, not only from the standpoint of chemistry, but also biological systems. The equilibrium's everywhere. Let's start with a definition. All right, equilibrium is defined as a dynamic process where a property is held constant as forward and reverse rates become equal. So I'll say that for you one more time. It's a dynamic process where a property is held constant as forward and reverse rates become equal. So what are the important parts of this definition that are going to help us just with our physical understanding about what equilibrium is? It's a dynamic process. And so what that means is even though there's some equality, even though there's something that looks static, there's actually motion, okay? Dynamic implies that there's some motion there. So how is it a dynamic process where something's equal? Well, it's a reversible process. It's a process that has both a forward and reverse component. And if you have things moving in one direction and an equal number of things moving the other direction, then what you'll end up with is something that's being held equal while things are still moving. Okay. And we actually saw an example of this earlier in the semester. We didn't really focus in on it a ton because we weren't really worried about equilibrium at that point. But earlier in the semester, we talked about vapor pressure. And we made this picture with vapor pressure where we thought we had like a liquid in a beaker and there are liquid particles down here. And these are the same particles up in the vapor phase. But I'm just going to draw them as open circles just to kind of differentiate them between their two states. So when we talked about vapor pressure, okay, so a vapor pressure is kind of set at a certain temperature. And what I mean by that is that implies that this liquid is only putting up into the vapor phase a certain amount of particles. So it looks like that vapor pressure is a static quantity, okay? But it doesn't mean that there's a set vapor and there's a set liquid and there's no motion. What it means is that once that vapor pressure is established, the amount going up into the vapor and the amount coming back down into the liquid phase, right? Those are equal over a certain time frame, okay? The forward and reverse rates are equal. Something looks static, the number of particles here, making a certain vapor pressure, okay? Something looks static, but really there's motion. It's just that there's equal and opposite motion, okay? So in terms of chemical equilibrium, right, or a chemical reaction, what's this thing that's actually being held constant? So to introduce this idea, right, let's just kind of write in a little example here. The way that we're going to view reactions now, and let's actually give these states because they'll become important. The way that we're going to view reactions is that they don't just occur in one direction. All right. We're going to start to draw this double arrow that implies that they're multidirectional. There's a forward and there's a reverse way of doing the reaction, right? So what's held constant at equilibrium? What's held constant is this thing that we're going to call K. And this is the equilibrium constant, right? Now you might see this labeled as a Kc. When we use pressures, we'll label it as a Kp, and you might see it labeled as a Keq, okay? All of these mean the same thing, right? And I will differentiate between when we're using a Kp or a Kc later on. They're getting at the same information. We're just using different sort of variables to calculate them, right? But whenever we see a big K, and it's not like a rate constant K, it's a big K, it's a different K, right? Whenever you see this, this is the thing that's held constant at equilibrium. The way that you view this is it's like our target. The reaction is trying to hit K. So any equilibrium, K is where it wants to be. It wants to be at that situation where the forward and reverse rates are equal to each other and you just have this value being constant. Okay, so then what is this K? What is this rate constant? Well, mathematically, it turns out that what you do to figure out what K is you look at species that could possibly have a concentration, and there's going to be more on that later, but you look at species that could possibly have a concentration like gases and aqueous species, and what you do is you write K by taking, all right, the product concentrations, right, over the reactant concentrations, right? The product concentration over the reactant concentrations. The only thing that sort of happens when things get complicated is let's put a stoichiometric coefficient here, right? When we write our K expressions, and these are the things that are held constant, this is the target we're trying to get to for a reaction. When we put in an actual stoichiometric coefficient, it becomes a superscript, it becomes an exponent, right? So C would have a 1 as its exponent because it's a 1 for the stoichiometric coefficient, and this concentration of B would have a 1 as well because of its a stoichiometric coefficient implied to be 1, all right? This is K, and like I said before, you'll see this label as a KEQ or it's a KC. Whenever you see KC, what we're doing is we're differentiating between Ks using different units, all right? And so KC implies that we're using concentration units over here, right? So important things about K and how we're going to actually do this is, again, this form kind of is maintained no matter what. Product concentrations raised to their stoichiometric coefficient over reactant concentrations all multiplied together, but also raised to their stoichiometric coefficients. The other forms of K are things like Kp. Right. And for this reaction, we could also get a Kp. Let me just make sure you can see that. Okay, good. And what Kp is it uses pressures instead of concentrations. So for this reaction here, we would write it as the pressure of C over the pressure of A squared because of the stoichiometric coefficient and the pressure of B. Okay. So the difference between Kp and Kc is what you use in terms of like the actual values for quantifying the species. Kp uses pressures, Kc uses concentrations, but hopefully you can kind of see this the same functional form. All right. So let's just practice one more and then talk about an important idea with writing these K expressions. So one other example here, let's say that we have some species that's in a solid form, and then this species that's aqueous, and we're in equilibrium with this species that's a liquid. Okay. Ooh, 3B. Let's make that 3B. That's aqueous. All right. Remember, one of the things that we said when we introduced the equilibrium constant was this idea that only things that could possibly have a concentration go into it, right? Species that are solids and species that are liquids, they don't have concentrations, okay? Now, there's some math that happens in the background that we're skipping over again, but what you need to know about these is that they don't have concentrations, so they won't show up as affecting our equilibrium. What we say from a formal perspective is that they have activities that equal 1. And that's more important for majors when we get to our junior year. But what this tells us is, what is the activity? Just kind of see it as a stand-in for concentration. What this means is when we build our K expression for this, whenever you see a solid or liquid, you just replace it with 1, right? So if I think about making our K C for this situation, right, using concentration, I would normally put the product here and raise it to the first power, but I notice it has a state where its activity is 1. So instead of putting anything there related to concentration, which doesn't really make sense for a liquid, I'm going to put it as a 1. Same thing down here. I know I need A and B information multiplying each other, but for this A, right, its activity is 1. So I don't worry about concentration. I don't worry about building in some sort of thing that could even stand in for concentration when that concentration doesn't exist. B is aqueous. I can express aqueous situations as having a concentration. So what I'm going to do is I'm going to express B as a concentration, and I'm going to raise it to the stoichiometric coefficient. Okay. So that's all for this video. We're going to get into actually using this in a mathematical way to predict movement within an equilibrium system next time.